Hi, today we're going to talk about a charging capacitor and its importance in electronics. Before us we have a 555 timer circuit. This one's in what's known as an astable multi-vibrator configuration. There's a mathematical equation that describes the voltage across a charging capacitor. And that mathematical equation, V inst, which stands for the voltage at any instant in time, is equal to V max, that's the maximum voltage or supply voltage, in brackets 1 minus E to a power of minus T, T stands for time, over CR in brackets. A typical circuit, as I've shown you on a 555 timer, would look like this. VCC, the supply voltage, is equal to Vmax, like that there. Then we have a resistor and a capacitor, like so. And the resistor is R in our equation, and the capacitor is C in our equation. The voltage we're trying to find will be applied at this point here. I'm going to have a go at drawing a graph. I'm not very good with this graphics pen just yet. If we have a graph like this, T moves in this direction and V instantaneous in this direction here, and at the moment of switch on, at the very moment we switch the circuit on, there is no voltage at this point. At the very minute you switch, the very second microsecond you switch the circuit on, C is effectively a short circuit down to ground, so there's no voltage across it. But from that moment onwards, the voltage at C, across C, begins to rise. And you get a graph that might look like this, if I can just get it right. Just like that, something like that. So at the top of the graph we can see the voltage across C flat lines, and this voltage at this point will be the maximum voltage. And once C charges to its maximum voltage, no further current flows. In any circuit of this type, R and C form a relationship known as a time constant. C times R is equal to a time constant. And in our equation, it's this CR here which forms a part of the power to E. It takes 5 time constants for our circuit to fully charge. There, 5 time constants. Forgive my drawing, it really is appalling. But after 5 time constants, the circuit's... Let's put this all into action now. We're going to imagine that R and C have a time constant of 1 second. And we're going to find the voltage across C after 1 second. And just doing this to make it easy, effectively C and R could be any time constant, and we could try to find the voltage across C for any given time, but this is just to make the mechanics of it easy. So we're trying to find V instantaneous here. So V instantaneous is equal to V max. Now for this circuit we're going to make V max equal 5 volts like that. So we can write 5 volts into our equation. And the next part in brackets is of course 1 minus E. Now we said we were going to find the voltage after 1 second. So T is 1, and we said that we would make the time constant 1 as well. So the power to E effectively becomes -1, like this. like so. At this point we can go to an online calculator. There's lots there, but I'm going to use this one. And what we want to do is we want to find e to the power of -1. So you can type in e. This little command here gives you a power to the -1 equals, and we see it equals 0.367. We'll just go to 3 significant places, 0.367. So we have 5 in brackets 1 to the minus 0.367 in brackets, and you multiply these brackets out. So 5 minus, and 5 times 0.367. I'll quickly do it on the online calculator. Multiply that by 5, and that gives us 1.839. And when we take the sum away, so we've got 5 minus 1.839. We get a voltage of 3.161 volts. Like so. And you could then do that for each of these time constants here. So I've done it for one time constant. The next time constant would be e to the -2. The next time constant would be e to the -3, e to the -4, e to the -5. And for each of those you'll get an instantaneous voltage, and you can plot that on a graph. It's much easier to do it in Excel, but we haven't really got time to investigate that here today. If you wanted to do a lot of these values, the best way to do this is to figure out a formula in Excel, a spreadsheet formula, and it will map it all out for you. It's the easiest way to do it. So that deals with the voltage side of things here. And now we're going to move on very briefly to current. Coming back to our circuit, which I'll draw up here, this time I'm going to include some values in our circuit. We said that C times R would equal 1 second. So if we had, for example, if R was 10k and C was 100 microfarads, then together these two would have a time constant of 1 second. Now, where current's concerned, this is important because we need to find the maximum current in this circuit. At the instant of switch on, all of the current in this circuit depends upon the voltage dropped across this resistor here. So we have, in our other circuit, we have 5 volts dropped across this resistor. And Ohm's law tells us that the current in a circuit, I, is equal to V over R, is equal to, obviously, the voltage, which is 5, divided by 10,000 in this case. And just go onto the calculator to find that out. So the maximum current in this circuit will be 5 microamps. Like so. Once again, there's a mathematical relationship. I instantaneous is equal to I max times e to the power of minus t over CR. An interesting way of comparing current and voltage in this type of circuit would be to take the same samples that we did for voltage and see what happens to the current. Now we know I max is a constant in this circuit. It's going to be 5 microamps, and the powers will be e to the -1, -2, -3, -4 and -5. We already know that e to the power of minus 1 is 0.367. So we can start off with 5 microamps times 0.367. So after one time constant, the current in this circuit will equal 183 microamps. Now, here's the thing. You can do the same thing for e to the minus 2, minus 3, minus 4, minus 5. If you find the percentage of maximum current, you will find that the current after one time constant is equal to about 36.3% of its maximum value. That's for current. After one time constant, the instantaneous voltage, if you do the same procedure, you'll find it's about 63.7% of its maximum value. And these two together make 100%. This relationship between current and voltage is always preserved. So, for example, if the voltage across the capacitor is 50%, then the current flowing through the circuit will be 50% of its maximum value. Eventually, when the instantaneous voltage reaches Vmax, no further current will flow in the circuit. And if you were to graph this, once again Excel is the best way of doing it, you will see that the voltage rises rapidly at first, of course, until it reaches its maximum value, exponential growth curve, and the current falls by the same amount. We can try and draw that. I'm not very good at drawing on this yet. It should really be going down the bottom there, but I've cocked it up. Anyway, there we are. So it kind of looks like a fishtail, doesn't it? It always looks like a fishtail to me anyway, like that. So current starts out at its maximum value, voltage starts out at its minimum value, and that effectively describes the relationship between current and voltage in a circuit containing a charging capacitor. Okay, got any questions or anything you want to discuss? I'm happy to answer them. Bye bye.